Jai Hind to all of you. I am Dr. Ritish Kumar and going to give the lecture on the radar topic, which is in the subject of microwave and radar engineering. So, what is the radar? The full form of the radar is radio detection and ranging. So, you can detect the target with the help of radio waves, we can say. So, first of all, we need to understand the frequency spectrum of the electromagnetic waves. So, let's begin with the frequency spectrum. There are various kind of frequency we have for a different bands, such as we can start from high frequency, very high frequency, ultra high frequency band, L band, S band, C band, X band, Ku band, K and Ka band, and all kind of bands has different applications which we have specified in the table. So the range for the means L band we can say 1 to 2 gigahertz, and S band 2 to 4 gigahertz, C band 4 to 8 gigahertz, X band 8 to 12 gigahertz, and Ku band 12 to 18, 18 to 27, 27 to 14, etc. So broadly we can say the range of the microwave bands lies is from 300 megahertz to 300 gigahertz, and these band we can split in two parts. The first one is 300 megahertz to 30 gigahertz, then 30 gigahertz to 300 gigahertz, and this band which lie from 30 gigahertz and to 300 gigahertz can say we the name of this band is millimeter wave bands, and this band is mainly used for the radar experiment and radar application broadly, and the K band, which is very useful for the application of satellite communication, and very high frequency band and ultra high frequency band mainly used for the television and frequency modulation broadcast applications. So these frequency bands are very important to understand the what kind of band lies for different frequency range. So most probably for the radar application the most important band is millimeter wave band, we can say. So let's begin the topic of radar. As I already told you about radar stands for radio detection and ranging. As the name suggests, you can detect the target with the help of radio waves. So this is the basic block diagram of radar. So you can look it here. So this is a transmitter. The radar has some block elements. The first one is the this is antenna, we can say, and this is transmitter, receiver, then signal processor, data processor, display, and this one is the target. So with the help of this basic block diagram we can explain the working mechanism of the radar. So you can clearly see here this antenna can be used as a transmitter and receiver as well. At a time you can use this antenna as a transmitter, and some different time you can use this antenna as a receiver. So this kind of antenna we can say transceiver antenna, and with the help of duplexer switch, duplexer is nothing but it is a kind of switch which can switch from transmitter to receiver. So you can make this antenna as a transmitter application with the help of this duplexer switch, and receiver again with the help of this duplexer switch. So first of all we need to understand what kind of antenna we can use for the purpose of radar application. As you can see, this is a kind of parabolic antenna, and it has the specialty to produce the directional beam. So and we can say this is a kind of directional antenna. So for the radar application we need to have very high gain antenna with very high directionality. It has suppose if for the directionality point of view, the antenna has in terms of direction, we can say the FBR of the antenna, that is nothing but front to back ratio, should be as high as possible. That is front power. This is front power to the, it is the ratio of front power to the back power. So to have the high directionality, the antenna should have as high as possible FBR ratio. In other terms, in terms of beam, we can say this is a kind of if I draw the radiation pattern of the antenna, this is kind of radiation pattern, right? So this is a main beam, this is main lobe of the pattern, and this is the back lobe of the pattern. As I hope this is a, you can clear the, you know the pattern of the antenna. So this is a kind of, how can you how can you correlate the beam width of the antenna in terms of directionality? If the directionality of the antenna is high, this beam should be as low, as narrow as possible, right? So you can specify the beam width with the help of the parameter half power beam width. So to have high directional antenna, you should have the half power beam width as low as possible, as low as possible. So for the radar application point of view, you should have the high directional antenna and high gain antenna as well. So you can see this is a target here, and once you transmit the signal from the antenna to detect the target, this is the intensity of the transmitter's transmitting signal, and this is the echo signal. What is the echo signal? The signal which is reflected from the target and received by the radar antenna is called the echo signal. So this is a echo signal which is a reflected signal from the target, and it has the intensity low as compared to the transmitted signal. As you can see clearly here, this is a high intensity signal and this is a low intensity signal. So at the time of echo signal, this antenna should be work as an receiver antenna. So once the signal is detected by this antenna, this duplexer switch is switches from this transmitter to this receiver, and this signal received by the receiver, and what kind of signal, whatever the signal you will receive at the time of receiver, you have to do some signal processing. Suppose you need to improve the SNR, as I can say, for the general communication of point of view, SNR, what should be the value of SNR? Means signal to noise ratio, signal power to the noise power. So your aim is to increase the signal power as high as possible, and you have to eliminate or reduce the noise power as low as possible. At last you will get, you need to have the signal to noise ratio as high as possible. You need to remove the noise whatever you are receiving at the time of the communication point of view. So you have to do some signal processing over here. So you can include the filters such as meshed filter and whatever filter you will design to reduce the noise, you can add it in the signal processor. And whatever the after doing the signal processing, whatever the result you will get, you can display with the help of data processor on a display device. So what kind of data you can receive? Suppose you can identify or you can find the size of the target, you can find the properties of the target such as size, mean and distance of the target, and the material of the target, the environment of the media, etc. You can find the properties of all the media and medium and the target as well. So this is a basic block diagram description of the radar. So you can have different kind of targets, such as in terms of velocity point of view, the moving target you have and some stationary target you have. So whatever the echo signal you are receiving from the stationary target, such as natural targets, such as means mountain, trees, seas, and words, etc. So these kind of noise, these kind of echo signals are known as radar clutter. Radar clutter. So I hope this radar clutter definition clear to all of you. Now the next is the main property of the target, the distance, the radar range, that is distance from the transmitter to the target, you need to find out with the help of radar range equation. So first you need to understand how we can find the radar range equations. So you can see, I can explain it with the help of this diagram. So suppose this is a transmitter antenna and it has the transmitter power PT and gain is GT, right, and it has some area, that is effective aperture area A, we can say, and this target has some radar cross section area, we can say it is specified with the sigma meter square. So this is the properties that we have for transmitting antenna and radar cross section area, right. So if I found the power density at a distance of r from the transmitting antenna, so we can say for the isotropic antenna the power density should be Pt divided by 4 pi r square. Pt is the transmitting power of the transmitting antenna and this is the surface area of the at a distance of r, that is 4 pi r square. So power density is equal to Pt upon 4 pi r square watt per meter square. And to have the because we are using the directional antenna here and it has the gain is equal to G we have. So at last we can say that the power density in the directional, for the directional antenna, it should be multiplied by the gain of the antenna, that is Pt Gt upon 4 pi r square. And now due to the power density of the echo signal, so we can say we can have the radar cross section area sigma meter square, and what kind, how many percentage of the power is reflected from this radar cross section area sigma square. Suppose you have a total area is 4 pi r square and radar cross section area has the sigma meter square area, then how much power is reflected from the this target, you can say sigma upon 4 pi r square percentage of power is reflected from this target. So you need to multiply this factor with the power density of the transmitting signal. So you can see this is the power density of the directional antenna in a particular direction is given by Pt G upon 4 pi r square, and you need to multiply this factor with this power density. So by multiplying this factor you can achieve the power density of echo signal here. And you can say because the power is received by this echo signal is received by the received antenna and it has some effective aperture area. Suppose this is total area of the antenna you have, and the signal you are receiving in this particular antenna, in this area of the particular antenna. So this is a effective aperture area that you are using in the receiving case, and total area of the antenna is this area. So in the case of received power signal, you need to multiply the factor of A, that is of effective aperture area of the antenna. So at last the received power you can have PR is equal to PT GT upon 4 pi r square upon into sigma upon 4 pi r square into A. So this area of a effective aperture area of the antenna you have, and this it has a formula is equal to AE is equal to 4 pi r square 4 pi upon lambda square into in the next slide you can see G is equal to 4 pi upon lambda square into AE, right? You can have. So after putting this value gain into this formula, you will have the another equation, and with the help of this equation you can find the radius, means distance of the target. So that is you can have R maximum is equal to PT G A sigma upon 4 pi r square. S minimum is to the power 1 by 4. Here S minimum is the minimum detectable power. So as you can say, as the target moves away from the radar, the intensity of the received signal is getting decreased. So it has some maximum range from which the radar can detect the minimum power, we can say. So you can have the minimum detectable power with the help of this equation as well. So these two equations are very important to understand this radar range of the radar range equation. This equation is known as radar range equation, and with the help of this equation you can get the location and distance of the target from the transmitting antenna. I hope this radar range equation is clear to all of you. Next is what is the Doppler radar? As we can say, the Doppler radar means there should be some shifting in the frequency when, in the transmitting signal and receive signal, and this shifting in the frequency is known as Doppler shift, and in terms of frequency we can say Doppler frequency shift. So as we can say, when the target is stationary, the frequency of received echo signal is constant. However, when the target is moving, the frequency of the received echoes is found to be different from the transmitted signal. As we know, if the target approaches the radar, the frequency increases, and if the target moves away from the radar, the frequency is getting decreased. So this is the basic concept of Doppler radar. So with how can we find the Doppler shift with the help of some mathematical point of view? So this is a as we know, omega is equal to 2 pi ft. This is the radial frequency, we have 2 pi f, and this is, as we know, phi is equal to omega t. So omega is equal to d phi by dt we have. So phi is equal to phase difference, and as we know how much phase difference is equal to 2 pi by upon lambda into path difference, and total signal is traveled from transmitting to target and target to transmitting is delta s is equal to 2r. So 2 pi by lambda into 2r, and at last we have 4 pi r upon lambda. So you can replace this phi with this value d 4 pi r upon lambda, and you can take the constant out from this differential part. So this is 4 pi upon lambda dr by dt, and this is the rate of change in the distance. As we can say, this is a mean velocity of the target, 4 pi b upon lambda, as we can write br upon lambda. Here fd is the Doppler frequency shift in the Doppler frequency. Vr is the relative velocity of the target with respect to the radar, that is dr by dt. Lambda is equal to wavelength in the meters. So suppose this is a target, we have it is moving in this direction with the velocity of b, and this is a radar, and this target is moving the angle, is making the angle with this transmitting antenna is theta. So it is having the direction this, and in this direction it has the velocity v cos theta. So we can say Vr is equal to v cos theta. So you can replace this Vr with the Vr is equal to v cos theta here. So Fd is equal to twice v cos theta upon lambda. So at theta is equal, at theta is equal to 0 degree, the Doppler frequency is maximum, we can say, because cos theta has the maximum value at 0 degree, and theta is equal to at 90 degree, the frequency shift should be 0. We can say this is the condition of when the trajectory is perpendicular to the radar line of the sight. So we can say what is the Doppler shift. Doppler shift is achieving in the case of moving target only. So suppose if the target is stationary, then Doppler shift in the frequency should be 0. We can say the Doppler shift should be constant, in other words. And if the target is moving towards the radar antenna, then the frequency is getting increased in that case, and if the target is moving away from the antenna, radar antenna, then in this case the frequency will be decreased, right. So this is the shift in the frequency, and this frequency shift is known as Doppler shift. So I hope these all the topics. The first one is the frequency bands, then the radar block diagram, and then the Doppler shift in the frequency will be clear to all of you. So thank you everyone.